gotta make the introduction to without much ado. Talking about high-speed packet filtering and from CLOUDFLARE from the London office. Welcome to DEF CON, and my pleasure to introduce you to Gilberto Bertin.
Thank you. Good morning. Thanks everyone for joining me today. Today we talk about past, present, and future of high-speed packet filtering on Linux. So let's get started. About me, I'm a system engineer at CLOUDFLARE. I work in the DDoS mitigation team in the London office. For the ones of you who don't know what CLOUDFLARE is a security and performance company which offers a reverse proxy CDN service. So when a site is on CLOUDFLARE, all its traffic is routed through our edge network first, and then it's proxied back to the origin servers. This means we can provide different services such as caching, content optimization, and most importantly, for the sake of this talk, we can provide DDoS mitigation. We have a fairly large network. We see a lot of traffic every day and also a lot of malicious traffic. And in fact, on a daily basis, we have to deal with hundreds of different DDoS attacks. And to give you some numbers, on a normal day, we see attacks ranging from 50 to 100 million packets per second and from 50 to 250 gigabits per second. But we have also seen much bigger attacks. This graph, for example, shows one of the biggest TCP SYN flows we recorded a few months ago. The green line represents the volume of the attack traffic, while the small yellow line at the bottom represents the alleged traffic. And the job of my team is to basically drop all the green traffic, because all the malicious traffic, before it hits our servers without affecting in any way the small portion of yellow traffic or alleged traffic. Okay, so let's start from Iptables. In the beginning, we were relying simply on Iptables to drop traffic. And Iptables is great for many reasons, because it's a well-known tool, it's relatively easy to interface with it from different programming languages. It has this nice concept of tables that hooks into different parts of the network stack and chains. It's also well integrated with the Linux kernel, and it has support for BPF matches, which means it's possible to use BPF bytecode to specify how a rule will be matched. And this gives Iptables a reasonable flexibility. And speaking of BPF, in the last 3 years, we've been developing a set of utilities called BPF tools, which allows to generate on the fly BPF bytecode to match a specific class of packets. In this example, I'm basically generating BPF bytecode to match a specific class of TCP SYN packets. And without going too much into the details, the weird string that you can see passed to the BPF gen command is called POF signature, and it's basically a short description of all the interesting fields of a TCP SYN packet. And the way we used to use Iptables is the following. We use the usual Iptable syntax to express most of the mitigation logic, and we resort to BPF to express those bits that cannot be expressed by just using Iptables. And this works great, but there is a problem. With Iptables, we can't handle big packet flows. And last time we checked, we could do 2-3 million packets per second on a single box, leaving no CPU at all to the user space applications. And this is for us a problem, because on our network, each server which serves HTTP and DNS traffic also participates in DDoS mitigation. So we can't just afford to spend a whole box just mitigating DDoS attacks. There are a few Linux alternatives, but we didn't really consider any of them. And the reason is that we are not just trying to squeeze some more million packets per second of DDoS mitigation capacity. We'd like to have a solution that we can use that uses as little CPU as possible to filter packets at line rate. So before discussing our current setup, I'd like to give you a quick introduction about the path of a network packet in the Linux kernel. And this is to make it clear why it's so expensive to filter packet by just using Iptables. So first, let me define a couple of important data types that I will refer later during the talk. So when I speak about packet buffers, the one at the bottom, I'm just referring to memory pages which contain the actual network packet. When I'm speaking about skbuf, I'm speaking about a big data structure that contains a lot of metadata related to a single packet buffer. So basically, it's just a structure that keeps the context about a specific packet while the packet is being processed by the network stack. And when I'm speaking about RX rings, the one on the NIC diagram, I'm speaking about data structures used by the network card to keep track of all the packet buffers that are actually in use. Okay, so how does Linux receive packets? Linux uses a mechanism based on polling. So basically, periodically, Linux invokes the netRx action and goes through the list of network cards. And for each network card, it checks if there are new packets. And the important point of this slide is that just the network driver has to do a lot of expensive operation, memory operation, to deal with the packets. It has to DMA and map the packet, allocate an SK buffer, and allocate a new page for a new packet that will replace the old one, and actually process the packet, and in the end, free all these data structures. So there is a lot of memory pressure just from the point of view of the driver. So I want to really quickly go through this call trace of the network stack receiving a packet, just to give you again a quick sense of how many operations the network stack does when it receives a packet, and so why it's so expensive to actually drop them. So as I said, netRx action is called periodically, which goes through, which calls the driver function, and we have to allocate SK buffers, and there is some generic receive offload processing, and this is repeated for each packet. Then the driver has to allocate new pages for the new packet that will arrive, and there is IP header processing, Iptables, row contract, and more contracting, routing decision. Finally, we encounter the Iptables chain, which is fairly late in this whole list of calls. And finally, layer 4 protocol handling, and I omitting other things that we don't care here. So what's the point of this? The point is that we should not say that Iptables is slow. We should say that Iptables is just executed too late into the network stack. And we have to do all these actions for each packet that we are going to drop. And that's why it's so expensive to drop packets. And so we should move to our current solution, which is based on user space offload. And when I say user space offload, I mean offloading to user space the task of dropping the packets. So user space offload is based on a technique called kernel bypass. Kernel bypass means taking some of the network card receive and transmission rings, mapping them in user space, and allowing a user space program to deal with them. So basically, partially the network card is detached from the network stack, from the Linux network stack, and the user space program can take control of that. So it can write packets from there and read packets from there. And one of the reasons this technique is used is to implement user space network stacks, because a user space program can just read and write packets from the NIC directly without having to deal with the kernel. But this technique is also useful to filter packets, because you can map a receive ring in user space, and a user space program can start reading all the packets from there without any interference from the kernel. And then the user space program can filter actually what are just buffers of packets. So the way this works is by just selectively offloading the attack traffic to a specific receive queue. And then after that, a user space program will be able to read the packets from the queue. And if the packet is a good one, it will just be reinjected into the network stack. And if it is a malicious one, there is nothing to do really because of the way this framework works. So instead of having to allocate and deallocate packet buffers like the Linux kernel does, this framework usually uses circular buffers. So there is no real work to do in case we are dropping packets. And since in case of big floods, we are dropping like 90%, 99% of the traffic, this is a big save in terms of performance. So we use a technique called partial kernel bypass because we keep the network card, most of the receive rings attached to the kernel network stack, and we bypass only a single or a couple of receive rings. And we use what is called an RX flow hash rule. So basically, we try to steer all the potential bad traffic to a RxQ, in this case RxQ N, and then we filter it. And when I say potential bad traffic, I mean, for example, traffic that is targeting a specific destination IP. So we can leave the kernel work on the normal traffic as usual, and we can filter in user space the bad traffic. So there are a bunch of different frameworks to do this that do more or less the same thing. And in fact, from the user space point of view, the way a user space filter is done is the following. So a user space program keeps asking the network card for new packets, and as soon as there is a new packet, the program goes through a list of rules, and if any of them is a drop, the packet is dropped, which means we do nothing. And if a packet is not a match for the rule, it means it's a good one, and so we reinject it in the network stack. So this solution works great because we can filter 6 to 8 million packets per second on a single core, compared to 2-3 million packets on a whole box. So this is a great performance gain. But unfortunately, there are some limitations about this solution because legit traffic has to be reinjected, and this can be sometimes expensive depending on the framework that we are using. One or more core have to be reserved completely for this kind of thing because the way we do it is by busy polling the NIC, and this is because we want to keep the latency as low as possible. And also you have to pay a lot of kernel space and user space context switches every time you move from kernel to your filtering user space program. And so the future, XDP, or Express Data Path. So XDP is a new technology recently introduced in the Linux kernel, and it's a concrete alternative to Iptables or user space offload. And the idea is to filter network packets as soon as they are received by the network card. So using an eBPF program, which will take as input a packet, and it will produce as output what is called an XDP action, which can be XDP pass, so the packet should proceed to the network stack, XDP drop, so the packet should be dropped, and there are even other actions and other cool things that you can do with XDP, but that we don't care today. So if you remember the 5 long slides called trace, this is where XDP is run. So just at the beginning, just as soon as you receive a packet inside the network driver. So before even allocating SKBs, you run your eBPF program, and you decide if you want to leave the packet flowing through the network stack, or you want to just drop it. And if we take a look at one of the drivers that implemented XDP, we can see how the XDP drop actions is actually similar to what we are already doing with user space offload. Because basically there is nothing to do. If you want to drop the packet, you just leave, you just do nothing. You just leave the packet buffer where it is in the network card ring, and you go to the next packet. So there is no memory allocation, the allocation cost at all. And yeah, so XDP has the same advantages as user space offload. There is no kernel processing involved, and there is no memory allocation and the allocation cost, no DMMA map and unmap cost, which is a very expensive operation. But also it has a couple of advantages because you can use it eBPF to program your filtering logic, and there is no need to reinject packets because if a packet is not going to be dropped, it will just go through the network stack the usual way. So let me spend a couple of words about eBPF. So eBPF is a kind of new, I think it is 2 years old technology in the Linux kernel, which is gaining more and more traction in multiple subsystems in the Linux kernel, for example, in the tracing subsystem. And it's an extension to the classical BPF, and it's close to a real CPU architecture, and in fact it's also JITted on many different architecture. But the great two things of eBPF is that it provides safe memory access guarantees and time-bounded execution. So when you load an eBPF program in your kernel, you know that it will be as safe as running a program in user space because the program cannot access random region in the kernel, and the program is guaranteed to terminate because no backward jumps are allowed. In fact, every time you load an eBPF program, the kernel will run a verifier, and if your program does not meet any of these guarantees, it is just rejected. And also, eBPF provides shared maps with user space, so you can have some kind of state shared between your XDP program and user space. And another great thing is that there is an LLVM backend compiler. So basically you can write your C program and compile it to eBPF and then load it in the kernel, which is super handy. And okay, so this is not an XTP tutorial, but I just wanted to show you a quick sample of an XTP program. In this case, this is a super simple example. And XTP program is the function that is called on each packet. It receives as input a context, which is just a couple of pointers to the begin and the end of the packet. And then we can just access the packet using the Linux kernel data structures that are already there. And so an important thing to notice is that we are actually making sure that the program is not reading past the buffers, the packet buffer boundaries. Otherwise, it will be not even possible to load the kernel, the program, because the kernel would comply. And then we can go on and check that the packet is an IP packet and access the IP header and make sure again that we are not writing past the buffers and return an action based on the filtering logic that we use. Okay, the second thing is maps. So I talked about maps, and they are super simple to use. So you define it, you define the size of the key, of the values, and the size of the map. And then using BPF helpers, you can just access a specific key and set the value. And so it's just like a normal hash table, and it's shared with userspace. And the great thing is that we can, of course, auto-generate XTP programs because it's just C. So it's easy to write a script and actually generate C code for you automatically. And in this case, I'm generating the same, the program for the same POF signature I showed you before with BPF tools. But instead of like outputting cryptic BPF bytecode, we can output actual C code and then compile it to eBPF and just load it. So I will not go through the whole code, but you can just you can access different header, the IP header, and the TCP fields that you are interested in. So if you are curious and you want to try it, the first thing to keep in mind is that XTP is a new technology, as I said, so it requires supporting drivers. So initially only the Mellanox card supported it, and now that at each kernel release there are new drivers that get support for XTP. But starting from Linux 4.12, there is a new feature called generic XTP. So even if you don't have one of this nice network card, you can just run XTP on your laptop and just play with it and see how it works. There are some samples in the kernel directory, so in /sample/bpf you will find some XTP programs, and there are also a couple of libraries that will help you load and manage the XTP programs. And that's all for me. So questions? Yes.
How many filters can you load with XTP on that space?
So you, okay. How many filters can you load with XTP? XTP uses eBPF. eBPF has an hardcode size of 4,096 instructions. So as long as you can stay in that size of the program, you can chain multiple XTP functions, you can do whatever you want. You can even change that limit if you know what you're doing. But the idea is that you should try to keep the eBPF program short because it's running in kernel space. So you don't want to hang the whole kernel while processing packets.
Do you make a distinction for V4 packets and V6 packets? Are those two separate programs, or is it the same program?
This is up to you, but you can, for example, start processing different header and then check which version of IP you are dealing with and then call another function, because you can, it's just C, so you can chain multiple functions as you would write in C.
Did you explore Mangle and raw before going this whole route?
Can you repeat?
Did you explore Mangle and raw tables and IP tables before jumping out and doing the direct?
If I did...
the Mangle and raw chains, that happened before processing
no,
input?
this the two Iptables chain happened after XTP.
Okay.
Okay. No more questions. So thank you.